All right, I think I got everything all set up. So welcome back everyone to Math 3. I would like to remind us that we have completed everything involving Chapter 2 now. Homework due dates should be set up accordingly for those. So please make sure that you are keeping track of where we are and where you should be in the homework. So remember, homework is going to be still due the very next class. For anything that we have completed. You still have the ability to work on homeworks after they've been due. You just have that usual 5-point penalty that we've talked about several times in class. Before I begin today, I want to point out a few things. We'll be covering 3.1 and 3.2 today. So if you're in my Tuesday, Thursday class, that'll be due on April 2nd. If you're in the Monday, Wednesday class, that's going to be due on April 6th. And those are, of course, by midnight, 11:59 p.m. particularly. Also, you may have noticed over the past 4 or 5 days that something changed in the shells, that there was now a combined Chapter 2 test, and temporarily you were not, the Part A or Part B, one of the parts for Chapter 2, the due date had been rolled back to earlier in March, so it was unavailable. Because I've already had students take Part A for Chapter 2 test, several of you, I'm going to keep the Chapter 2 test separated because I don't want people doing 2 different versions of something. I don't think that's fair. However, since nobody has done the Chapter 3 test, since we haven't started Chapter 3 yet, we will be doing the combined test for that. So I'm going to go to Connect today, and I'm going to make the due date for the combined Chapter 2 test something you won't even have access to, and I'll just make sure you don't have access to it. So make sure that you are taking the separate test for Chapter 2, the Part A and Part B. And then when we get to Chapter 3, you will not take the Part A, Part B. So again, I'll make those unavailable. You'll take the combined Chapter 3 test. So that will be all 13 or 14 sections. You'll be allowed to use a calculator for the whole thing since it's all at home. But it does have to be your own work. So make sure that you are doing that. Anything else from up here? So again, Chapter 2, we're taking the split test. Chapter 3, we're taking the combined test. It would have been nice if they had made that combined test for everybody a little earlier, but we're in a unique situation right here. Everybody's doing 10 million things at once. So since we had already kind of gotten to that, we're just going to, again, take the split Chapter 2 test, combined Chapter 3 test. Now, please remember that you are allowed and will want to use a formula sheet for that, for both of those tests, in fact, as well as the final exam. But you'll have to print or use your own, and I mean, you can just pull it up as a PDF. There's no problem there. And I'll really quickly just show you how we get to that. So when we're in the home screen of Connect, and you have your course with all the folders, you go to Resources, and then Reference, or no, I'm sorry, it's a Course Files. Course Files. Course Files, and then the first, second, third, fourth thing down, you'll see formula sheets. You can download that PDF. You can then open it. If you have a printer at home, you can print it. Otherwise, you can just leave this up on your computer screen while you're testing. And look, here we have all those conversions from the end of Chapter 2. The first 4 being just units of length and the US system, but then you also see the same for here, just without the fractions. So honestly, this first one is unnecessary. You just need this big block for length, time, capacity, and weight, and that's all the US system. Then a little below that, we have the US to metric conversions, the same exact table we saw from our worksheets, the same exact table you would have needed for your homeworks. In between them, you have that line that helps us go between anything in the metric system. So the middle is your meters, grams, or liters, and then kilos at the far left, millis at the far right. You use your movements to tell what the decimal to do. Below that, you have your temperature formulas, all 4 versions as we saw in the workbook. Then we have our formulas from earlier in Chapter 2 dealing with sales tax, discount, interest, commission, percent change, which we said these percent change formulas are not really completely there, because we don't see anything that says what an amount of an increase or amount of a decrease is. You have to remember that that's the difference of the larger and the smaller. And then you also have to remember to convert these to a percent after you do that division. There's also some geometry formulas up here, most of which we will get to in this next chapter at the end. So again, your formula sheet, when you're in Connect, is under Resources, Course Files. It should be the fourth thing down. All right, so with that being said, let's get into the new material. So chapter 3. Chapter 1 was all about fractions. Everything in the wonderful world of fractions. We learned how to add, subtract, multiply, and divide them, and a whole bunch of other things. Then chapter 2 was decimals. We learned how to add, subtract, multiply, and divide those, and a whole bunch of other things. We also learned how to go between fractions and decimals in that chapter, as well as percents. We learned some applications, and we got into some dimensional analysis type things, some unit conversions and metric conversions, whether they were US or metric. And now chapter 3 is going to focus on two primary topics. Chapter 1 and 2 are kind of very focused. It's just fractions, just decimals. Chapter 3, the first half, is going to be dealing with our sign numbers. So we are now going to open ourselves to the idea that numbers are not just positive, they can be negative, kind of like debt would be negative, whereas savings would be a positive. But then in the later half of the chapter, we're going to deal with some very basic algebra, some solving of simple equations. Now, I know we've already solved one type of equation, but we'll now solve 4 different types of equations in this chapter. And then at the very end, we'll do some 2-dimensional and 3-dimensional geometry, some basic formulas using, well, the stuff we just saw over here. All these formulas. So volume, area, etc. So 3.1, starting off this journey into sign numbers, which honestly, there's no sign numbers in 3.1, but we're building up to it. Exponents and square roots. Now, we have seen exponents before in this course, but we're going to start using them a little more frequently. Whenever you have something multiplied by itself, and especially if it's multiplied by itself and then by itself and then by itself again, we don't want to have to always write out. It's like this, look at this number 1, 5 times 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 5. That is a whole lot of 5s. And it gets tedious to have to write them all out. Now, it's not wrong to write them all out. It's just tedious. So if we think back to when we introduced multiplication, we said that multiplication was for adding the same number over and over and over and over and over. If I wanted to add 3 plus 3 plus 3 plus 3 plus 3, I mean, yes, I can just do that straight up. 3, 3, 3, 3, and 3 adds to 15. But again, it was a little tedious having to write all these 3s. So that addition, which was repeated, the same number over and over and over, we introduced multiplication. So instead of having to write all these 3s, we just say, all right, we're adding this 3 several times. How many times? 1, 2, 3, 4, 5. So we're adding 3 5 times. And that's where the times comes from, because it's the number of times we're adding something over and over and over. And then we learn all about multiplication, and we see that 3 times 5 is 15. In other words, multiplication is an extension of addition. It's when you're adding the same number over and over and over. Well, comparatively, exponents are used for multiplying the same number over and over and over. So if you had, say, let's just do 4 of these this time. 3 times 3 times 3 times 3. I don't want this number to get too big. We're multiplying the same number over and over, and now only 4 of them, it didn't get that tedious, but if I had 10 more of these, again, it just gets tedious. If your vision's not great, you might lose count. All sorts of things can go wrong in the process of trying to figure out that this is, well, 81. 3 times 3 is 9, 9 times 3 is 27, 27 times 3 is 81. You can even group these 3s. You can multiply the first pair, 3 times 3 is 9. You can multiply the second pair, 3 times 3 is 9. And then 9 times 9 would be 81. So this is the multiplication version, which is repeated over and over and over. The exponent version what you do is the thing that's being written over and over and over, you'll write that as what we call the base. So the 3 is the base. And then the exponent, the number that's to the top right of that, is how many times you saw that 3 being multiplied by itself. There's 1, 2, 3, 4 of these. So that exponent is a 4. I'm just going to abbreviate. Oh, no, I don't have to. Sometimes I forget I can go off this margin. And 3 to the 4th is 81 because it's still 3 times 3 times 3 times 3. It's the exact same math. It's just a more compressed way of writing it. And this is going to be beneficial for us very, very often. And then we even saw this very early in chapter 1 when we talked about prime factorizations. And we wanted to reduce fractions. And we used it for a second, but then we stopped using it because we didn't learn all the rules of exponents yet. So again, most of this should feel like a repeat, pun unintended, of something we've done before. But we have to pay attention to the instructions for these problems because they're not always going to say evaluate. And in fact, look at this. For numbers 1, 2, and 3, it says do not evaluate. We're just changing forms. So you have to pay attention to the instructions in Connect, homework, quiz, test. If you actually did the evaluations on problem 1, 2, or 3, if let's say the answer number 2 is 12, if you wrote 12, it's going to mark it wrong because it wanted you to write 8 to some power or 3 to some power. So let's try this out. Write the repeated multiplication in exponential form, and again, do not evaluate. So we're going to count the 5s. I see 1, 2, 3, 4, 5, 6, 7, 8 of them. There are 8 of these 5s. So it's either going to be 5 to the 8th or 8 to the 5th. We have to make sure we get it in the right order, though. The base, the bigger number on the bottom, is the thing that was repeated over and over. The thing that's repeated over and over here is the 5, so the base has to be a 5. Then the exponent is that number that's a little smaller and kind of sitting at the top right of the 5. That's how many 5s we have. There's 1, 2, 3, 4, 5, 6, 7, 8 of them again. So that would be equal to 5 to the 8th. That is the exponential form for 5 times 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 5. So you're just counting how many of them there are, and that's the exponent. The base is the thing that's being multiplied over and over. So for problem 2, we have 8 being repeated over and over. So the base is an 8. And there are 1, 2, 3 of them. So that's 8 to the 3rd. Now again, I don't need to know what 8 to the 3rd is. I'm not asking you what 8 to the 3rd is. All I've asked you to do, all Connect has asked you to do, is to write it in exponential form. Yes, 8 to the 3rd happens to be 512, but I don't care, Connect doesn't care in regards to this problem. Number 3, 9, 9, 9, 9, 11, 11, 11. Wait a minute, this is different. There's a little separation here. Here's a bunch of 9s, here's a bunch of 11s, and now fun fact, they don't have to be grouped this way. It could be 9, 11, 9, 9, 11, 9, 11. So you might want to group them if that were the case so that you can more easily count them. So this little squiggle is just me visually separating it. I'm going to erase it though, just so you don't think it's part of the problem. So let's see, I've got 1, 2, 3, 4 of these 9s. So that's a 9 raised to the 4th. I'm going to switch colors just for emphasis, but this is still part of the same problem, times. And then we've got 1, 2, 3 of these 11s. So we need an 11 to the 3rd. If they're not all the same number, you can't just write it as a single base in an exponent. And that's all we can do. We can't do anything else since they asked us to not evaluate it. Now again, if you're curious, I'm just going to do this really quick. 9, 9, 9, 9 times 11 times 11 times 11. That answer is, unless I goofed, 8,732,691. Yes, that is correct. But again, that wasn't the point of the problem. The point of the problem was to just write it in exponential form. When we get to problems 4 through 6, they say to expand the exponential expression as a repeated multiplication do not simplify. So just like last time, we're not going to find out what the actual numerical answer, whether it's 8,732,691 or it's 7. We just want to write this over and over and over, and we want to write the base over and over and over as many times as we have to. So for problem 4, with a base of 6, that means we're going to write a bunch of 6s. How many 6s are we going to write? Well, there's a 7 here, so that's how many 6s we should write. This will be 6 times 6 times 6 times 6. That's 4 of them. Here's a 5th one. Here's a 6th one. And here's a 7th one. Let's double check the count. 1, 2, 3, 4, 5, 6, 7. That would be 6 to the 7th. That's it. We stop there. Again, you have to be careful and you have to pay attention to the instructions and connect. It's going to break your heart if you get that 6 to the 7th as a multiplication correct, but they mark it wrong because you didn't do this. Similarly, for problem number 5, that's 10 to the 5th. So that means we're writing 10 over and over. Specifically, we need 5 of them. Here's 1, 2, 3, 4, 5 of them. And that's it. Problem 6, equally simple. 3 squared, that means we're taking the 3 and multiplying it over and over, but not a lot this time, just 2 of them. Exponential notation doesn't feel as useful when it's something like 3 squared because you're not really writing a lot less. But when you get into higher algebra, there can still be reasons to use that notation for simplifying bigger things, potentially. I don't necessarily mean bigger numbers, just a more complicated problem. So yeah, that answer is 9, but that's not what we want. If you wrote 9, Connect would mark it wrong. I would not give you partial credit on a homework. I would not give you partial credit on the test. You have to follow instructions. All right, so I'm gonna have to erase all of this so I can scroll down. Remember, these videos go up on YouTube the same day. I usually get them up within a half hour. It just takes about 10 minutes to create the file and another 20 minutes for YouTube to digitalize it, if you will. All right, and let's get off of annotate so we can scroll. So 7, 8, and 9. Now this says evaluate the expression. Evaluate means to actually find out what number this is going to be. So we're not going to write 5 to the 8th. We're not going to write 6 times 6 times 6 times 6 times 6 times 6 times 6. We're going to write, okay, well, for example, in number 6, 3 squared, 3 times 3 is 9. That's what we would write for 7, 8, and 9, the actual mathematical answer. So 5 squared, if you want to, you can rewrite this in the expanded format, which says we're repeating the 5s. There's 2 of them, so 5 times 5. If you don't have to do that based on your skill level, then you don't have to do that. That's okay. Some people will just say, oh, 5 squared in their head, that's 5 times 5, which is 25. Some people will write out the expansion to get to the answer. And per usual, I don't care how much work you're showing necessarily, it's that you have the capability of getting there. Some people show more work than others. Some people show less work. But the answer is not 5 squared. The answer is not 5 times 5. It's 25. Anything else will be marked wrong. No partial credit. 8, 10 to the 4th. So again, if you choose to write this out in the expanded form, that says there's 4 of these 10s. So 10 times 10 times 10 times 10. Multiplying 10s means you can just stack the zeros. There's 1, 2, 3, 4 of those zeros. So that'd be 1, 2, 3, 4 of those zeros. I'll put a comma. So that's 10,000. And again, if you could go to 10 to the 4th, oh, that should just be 4 zeros on that. Same answer without the middleman. That's fine. Number 9, 2 to the 6th. That's 2 times 2 times 2, 2, 2, and 2. 1, 2, 3, 4, 5, 6 of them. I'll actually show the multiplication step by step this time, just in case anyone needs to see it. You might be able to verbally just go through it. 2 times 2 is 4, 4 times 2 is 8, etc., etc. I'll show all the work for this though. So I'm just going to multiply the first pair of 2's. So that 2 times 2 is 4. And then, wrong color. The rest of them, 1, 2, 3, 4 of them. So again, the dotted circle, that's the pair I actually multiplied to get the 4. And then the other 4 2's are just brought over. Well, now let me multiply the first pair of numbers. 4 times 2 is 8. So that's 8 times. And then there are the 3 2's left over. Then let's multiply the 8 and the 2, which is 16. And then we still have a pair of 2's left over. It's a little tedious changing color over and over like this, but I think it's worth it. Then let's multiply the 16 and the 2, which is 32, times the last remaining 2. And 32 times 2 is 64. Again, if you don't need to show all that work, you don't have to. Some people might just be able to double them in their head. 2, 4, 8, 16, 32, 64. Just make sure you do enough of them. Don't go too much. Don't go too little. 32, you would have been doing 2 to the 5th. If you got 128, that's 2 to the 7th. So take your time. Show the work that you have to show. So these are our exponents. This is not the only thing that we see exponents with. In fact, in the previous chapter, chapter 1, we were doing fractions with exponents. We had things like a half to the 3rd power, and we had to multiply the half times a half times a half. So again, I really feel like none of this is new, but it's something that we're going to continue to see, so they like to readdress it. All right, and I just realized I left my mouse in the other room. Okay. Clear. All right. Next up, square roots. Square roots are kind of like the opposite of having an exponent. The square root of a number means that we multiply the number times itself. To square a number means that we multiply the number times itself. So 3 squared was an earlier problem, and that was 9. That's the same thing as 3 to the 2nd power. Now, they talk about this positive square root. Let's not get too focused on that. To find a square root of a number means that we reverse this process. We're trying to find a number that when you multiply it by itself gives you the inside. So again, taking a square root, so like this square root of 49, let me scribble this 7 out for a second. If I ask you what the square root of 49 is, so this is the symbol for a square root. This is asking the square root of 49 right here. We're asking what number times itself is equal to 49. So initially what a lot of people have to do is just be systematic, and they'll say, okay, well, 2 times 2 is 4. So that's not it. 3 times 3 is 9. That's not it. 4 times 4 is 16. That's not it. 5 times 5 is 25. That's not it. 6 times 6 is 36. That's not it. 7 times 7 is 49. Oop, there it is. So we know that the square root of 49 is 7 because 7 squared, or 7 times itself, is 49. This is what's called an implicit problem. It's probably the first example of an implicit math that we come across, generally speaking. Implicit means it's kind of like Jeopardy. We have the answer and we're wondering what the question was. Because normally we're looking at something like 7 times 8 and it tells us exactly what to do. 7 times 8, we're taking 7 and we're multiplying it by itself 8 times, or we're adding 7 to itself 8 times. But the square root of, say, 81, this doesn't tell us exactly what to do and how to proceed. We're questioning, all right, I need to find a number that when I multiply it by itself is 81. We already made it up to 7, so let's just write a few more to the side. 8 times 8 would be 64. 9 times 9 would be 81. 10 times 10 would be 100. 11 times 11, 121. 12 times 12 is 144. And that is a 9 right here. 9 times 9 is 81. And then finally, 13 times 13 is 169. Now we're technically back into a no calculator section, even though we can't enforce that anymore, which is why we're doing the combined test. So I really do advise you to practice this stuff without a calculator, because moving forward in a more advanced math class, you might not be allowed a calculator depending on your teacher or course. So you should be able to do these on the fly as well as the previous 7. I'm not going to write all of those since we said them. But notice that we won't have the square root of 65. We won't have the square root of 70. We won't have the square root of 80. We don't know the square root of every single number in the world. There is actually very few square roots that we know in comparison to the ones that we don't know. But we generally just ask about the ones we know, or we get into more complicated math. So the square root of 81 is, we're looking for a number, and we multiply it by itself is 81. Well, we just said that 9 times 9 is 81. So the square root of 81 is 9, since 9 times 9 is 81, or 9 squared is 81. But again, this is the answer. This is just the logic, the work, if you will. So this would be good work to show for homework, quizzes, tests under normal conditions. The square root of 4, for problem 11, we're looking for a number times itself that makes 4. Well, 1 times 1 is 1. 2 times 2 is 4. Oh, there it is. So the square root of 4 is 2. And that's since 2 times itself is 4. Has to be the same number times itself. Do these last pair quickly. The square root of 36 is, well, 5 times 5 is 25. 6 times 6 is 36. So it's 6. Since 6 times 6, or 6 squared, is 36. And the square root of 169, we see over here, it was the last one I wrote, was 13. This is the last one that I suggest students memorize up to, because up to 13 are the ones that we see the most. I'm not saying that you won't ever see like the square root of 400, which would be 20, or anything bigger than that, just typical. And that's since 13 times 13 is 169. And that will close out 3.1. It's not a very long section, just 1 page of worksheets, in fact. I think there's only 2 sections in this whole book that are like that. Okay, so let's clear our screen. Let's go back off of annotate. Next section, signed numbers, what we were alluding to earlier that we'd get to. Sorry, I have something covering up part of my screen. There we go. All right, signed numbers. And this is 3.2. We've dealt with only positive numbers. We may have talked about a negative number once or twice, just in terms of magnitude, but we haven't gotten into the math with negatives. So if we have a number line, and we're just marking the integers of 0, 1, 2, 3, 4, 5 on the right, and then -1, -2, -3, -4, -5 on the left. These numbers go past -5 and +5. They go on to what we call infinity and negative infinity. They don't have to be marked in multiples of 1. You can go 0.1, 0.2, 0.3, 0.4, 0.5 up to 1. You can do this in multiples of 5 or 10, anything you like. But the important thing is that the negatives are on the left, and as you're moving left, it feels like they're getting bigger, but technically they're getting smaller. And the positives are to the right in a manner that we're used to. Now notice I said that the negative numbers, as you move left, it feels like they're getting bigger, but they're actually getting smaller. Remember, smaller numbers are always to the left on a number line. So -5 is actually smaller than -4. -4 is smaller than -1. -5 is smaller than +5. -4 is smaller than +1. You might say, oh, well, 4 is bigger than 1, but no. A -4 lies to the left of +1. So that's how we arrange our positive and negative numbers. And they say, write an integer that denotes each number. An integer is just saying if a number has a sign or not. Positive, no sign. Negative, you throw a little dash in front of it. All right, so we got this mountain, and I'm not going to try and pronounce that. The highest mountain in Australia is 2,228 meters above sea level. So that would be a positive number. Now, we normally don't write the positive here, but I'm just illustrating a point. That's 2,228 meters. That's what we mean by write an integer for that. Problem 2, the temperature in Vancouver, Canada decreased 27 degrees Fahrenheit. Decrease means to make smaller or to be negative as a number. So that would be a negative 27 degrees Fahrenheit. Make sure you're writing your units for problems like this. You might not have to type that, obviously, but if this was a handwritten test, those would be important. All right. I got to clear. Oh, I put it down here. That's right. Okay. Sorry, sometimes it takes a little longer to set up. Number 3, the credit bureau downgraded Kim's score by 383 points. Man, that is a big, big hurt on your credit score. Someone's not been paying their bills, might be experiencing some COVID-19 financial stresses, who knows? But downgraded means a decrease or a negative number. So that's a minus 383 points. Kevin's health insurance premium went up $28 a month. So that would be a positive $28 per month. Alex has no balance on his credit card account, which is exactly what we all want ultimately, or at least to not pay interest. You can have a balance temporarily as long as you pay it off every single month. And if you think you're supposed to have a balance, then the credit card companies have one, because that is completely wrong. And a tangent. So no balance means 0. So $0. That's it. All right. Nothing too crazy, just writing out signed numbers. All right, rational versus irrational numbers. This is the biggest thing that we want to focus on in here. We don't necessarily need to focus on the whole numbers versus the integers versus the rationals. To be a rational means that it is a terminating or repeating decimal. Oh, I need to annotate. So rational numbers means that they terminate or repeat as decimals. So 2/7 would repeat. 0.25 terminates. 0.3, and you can't really see it, so let me emphasize that there's a bar there. 0.3 repeats. All these integers terminate, all these whole numbers terminate. These are just subsets of numbers. And again, we're not going to focus on that too much. Rational numbers means they terminate or repeat as a decimal place. In other words, they can be written as a fraction. The irrational numbers, let me switch my color. Your irrational numbers, oops. Means they are non-terminating, non-repeating. Typically, square roots, we don't know. So if you take the square root of 4, or sorry, if we asked you what the square root of 4 is, because we can take it, the square root of 4 is 2, that would be a rational, the green one. But if we asked you what the square, or sorry, if we asked you what the square root of 5 is in terms of classification, we don't know the square root of 5 because there's no number times itself that makes 5, no whole number at least. So that makes it irrational. So if you see a square root and you can't take the square root, that's irrational. Also, pi is irrational because it's non-terminating, non-repeating. 3.14159, I believe 2, and then a whole bunch of other numbers that I don't have memorized. So rational means they terminate or repeat. Irrational means they do neither of those things. And the most common types of irrational numbers are square roots we can't take and pi. All right. So for problem 6 and 7, number 6, we're just going to put the numbers on the number line. 7, we're going to classify them as a rational or an irrational. So locate the number on the line, and when I put my little dots, I'm going to mark them with A, B, C, or whatever is relevant for the problem. So -9, that's not over here. This is +9. It's over here. So this would be A. B, +5, is over here. +5, not -5. 11 is right here. That's C. D is 0, dead center. E is -8. Since it's negative, we're going left. This point right here is E. F is +9. And there we go. Nothing too crazy there. Problem 7 says to identify the number as rational or irrational. -3/7, well, this is a fraction, which means it's rational. Remember, rational numbers are fractions or decimals, but as decimals, they terminate or repeat. For problem B, now this is a square root, and this is where we said if you can take it, it's rational. If you can't, it's irrational. Well, we said earlier the square root of 25 is 5, which means this is rational. That's an N. Rational, not an M. Square root of 10, I don't know a number that when we multiply it by itself to get 10. So that makes it irrational, because we can't take the square root. 7.8, that terminates, so it's rational. I'm just going to abbreviate now. -17, that terminates. It's a whole number. In fact, excuse me, it is not a whole number. It is an integer because it's negative. It's not whole. And again, I'm not going to ask you those questions. So it's rational. D, now this extra 3 outside is irrelevant. It's all about the square root of 2. Square root of 2, we don't know a number that multiplies by itself to make 2. So we have no idea what that is, making it irrational. All right. Let's go down some more. Let me pull this back just a little bit so I don't have to. There we go. Perfect. Because that should still be readable. Place the correct symbol less than or greater than between the two numbers. So 5 versus -10. So you got to think about where these would fall on a number line. And drawing up the number line might even be helpful. So let's just put a 0 here. Let's go right 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm doing this super quick. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And I'm not going to label every single one. So 5 would be here. 1, 2, 3, 4, 5. So 5 is right here. The -10 is over here. Now the -10 is to the left, so -10 is the smaller number. So -10 is smaller, which means 5 is greater than -10. So 5, oops. It's greater than -10. -6 versus 0, with a -6, we're going left. 1, 2, 3, 4, 5, 6. So here's -6. 0 is dead center, splitting the positives and negatives. -6 falls to the left of 0, so that means -6 is smaller. So we're going to use the less than symbol. So again, we use the less than symbol. I'm just having to erase my points each time so it doesn't get too clustered, but I'm going back and writing the answer. -5 versus -9/2. So -5 is over here, 1, 2, 3, 4, 5, going left 5. That's the -5. But this -9/2, it's a little tough to see where that is on something labeled only as whole numbers. So we probably need to label that -9/2 as a decimal or a mixed number. Let me erase that point for just a second. I'll go back and do that in a few. So -9/2, if you convert that to a decimal, that would be -4.5. Or as a mixed number, it would be -4.5, which means you're going left 1, 2, 3, 4 times, and then you're going to continue going left half of a time. So this right here, this dot, that is the -9/2. The -5 was going left 1, 2, 3, 4, 5 times, which is just barely to the left of that. So the -5 is to the left of the -9/2, which means -5 is smaller or less than. So when you have fractions that are improper, it is usually a good idea to convert them to mixed numbers or decimals so that you can actually tell the size. And I made that emphasis very heavily in chapter 1, that improper fractions, while useful for adding, subtracting, multiplying, and dividing, they kind of aren't great for gauging size. So that's why I converted it. And it didn't matter which one I converted to. Now I got to do a whole bunch of erasing. Actually, let me just switch colors. That's a lot. So for D, 2/9 versus -8. Now 2/9 is not an improper fraction. So that's less than 1, but more than 0. So it's 2/9 of the way to 1. So if you imagine splitting this thing up into ninths, it would just barely be to the right of it. So that's about 2/9. The -8 is way over here, going left 8 units. So the -8's to the left, which makes it the smaller number. But the 2/9 is on the left here. 2/9 is the greater number, so use the greater than symbol. Let me switch color one more time. Green. -3 versus -10/3. Well, -10/3 is improper, so let's convert that. 3 goes into 10 3 times with a remainder of 1, so that would be -3 1/3. Or if you like it as a decimal, -3.3 bar. So -3, starting at 0, goes left 1, 2, 3 times. Here's the -3. The -10/3 is going left 3 and then a third more, or left 3 and then 0.3 more. 0.3 repeated, excuse me. So left 1, 2, 3, but then a third between -3 and -4. So that dot right there, that would be our -10/3, which is to the left of the -3. So -3 is the greater number, so we use a greater than symbol for that. All right. So that's how we can order numbers. It is very often helpful to draw up a number line, but you don't want to have to do this if we're dealing with ridiculously large numbers. The biggest takeaway from here is that your improper fractions need to be converted to mixed numbers or decimals. Proper fractions, like 2/9, we can leave those alone. Those are between 0 and 1. If you were ever comparing two fractions to each other, remember back in chapter 1, you had to get an LCD, so that's still possible. All right, absolute values. This is an important concept, and we're going to talk about absolute values pretty frequently in here without actually calling them by name. When we get into adding and subtracting and multiplying and dividing sign numbers, very frequently we'll be using the idea of an absolute value. What does an absolute value do? It makes the number positive. That's all it does. That's what all this fancy stuff says. But we have to know our symbol. If we have a number and it looks like it's between an 11, but the ones are really stretched out vertically, well, that's our absolute value symbol, which just says to make the answer positive. An absolute value makes the answer positive. And let me not just say makes the answer, let's say makes the inside turn positive. There can be problems with absolute values that have negative answers, and that's because of something else going on. All right. So they get into, oh, absolute value is the distance from 0 to the point, and that is an excellent concept, but we're just going to think about it this way. It's going to take the inside number and turn it positive. So if it was already positive, it leaves it alone. If it was negative, it makes it positive. So down here with problem 9, A through D, determine the absolute value. Well, the absolute value of -3, since it's negative, it makes it positive. That's it. Notice I don't write the absolute value symbol anymore. Once you take the absolute value, that symbol is gone. Again, once you take that absolute value, the symbol is gone. For B, the absolute value of 0, 0 is what we call a signless number. It is neither positive nor negative. We kind of treat it as a positive a lot of the times, but it is technically neither. But that just means it doesn't have a negative, so the absolute value of 0 is 0. No more absolute value symbol. That's it. It's pretty easy. The absolute value of -2/17, well, since the inside has a negative, we're just going to throw it in the trash can, and then we get rid of the absolute value symbol. The absolute value of -2/17 is +2/17. The absolute value of -5.7, it doesn't matter if these are fractions or decimals, the absolute value just gets rid of the negative inside, if there is one. If there isn't one, do not put one in there, you just leave it gone. So I'm going to make an E for this problem, since I don't feel like they did a perfect job illustrating this. What if we had the absolute value of 32? The inside's positive, and the absolute value of a positive is a positive. So the absolute value of 32 is 32. The absolute value of -32 would have also been 32. So now none of these answers are negative, but that doesn't say that an absolute value problem can't lead to a negative. We will see a problem or two where that's going to happen. But that's because something else is going on outside. All right. So let's scroll down. Which is greater, the absolute value of -4.3, and we're not going to do all of these. Let's just do number 10. Which is greater, the absolute value of -4.3 or the absolute value of -7.2? Well, you have to take these first. The absolute value of -4.3 would be positive 4.3, and the absolute value of -7.2 would be positive 7.2. And if you put these on a number line, 4.3 would be to the left of 7.2. So that says that the negative, I'm sorry, I was about to say something wrong. The 4.3 lies to the left, which makes that the smaller number. They asked which one's greater, so the absolute value of -7.2 is greater. What I like about this problem is without the absolute values, -7.2 would have been less than -4.3. But when you take their absolute values, that whole idea of less than or greater tends to swap around. Not always, I said tends to. All right. Now let's get into the opposite of a number. Opposite kind of feels like absolute value. It kind of feels like absolute value. And that's because an opposite of a number means to change its sign. Opposite means to change the sign. Opposite means to change the sign. That was not the definition of absolute value. Absolute value said, make the sign of the inside positive. Opposite says change it. So when we take an absolute value, it always makes the inside positive whether it was negative or positive originally. So if it was positive originally, it doesn't change the sign. So opposite kind of feels like half of an absolute value, because sometimes absolute values change signs, sometimes they don't. Opposites always change signs. So to find the opposite, we're just changing the sign. For 14a, the opposite of negative 51 would be positive 51. That's not a question mark, that's a colon. Sometimes that happens with this marker. B, 6.4, its opposite would be negative 6.4. For C, it's starting out as negative 3/8, so its opposite would be positive 3/8. Doesn't matter if it's a fraction or a decimal, you're just changing the sign. The opposite of 0, well, if you call the 0 positive originally, its opposite would be negative 0, but there is no negative 0. Negative 0 is 0. So 0 is unique in that its opposite is itself. Problem 15 says to simplify. Now, they don't necessarily explain what it means to have this extra negative in the front. So 15a, we've got a negative and then another negative. Now, spoilers, this is really the idea of multiplying negatives, and we'll get into that in a later section. I don't want to say the rule yet, so I'm not confusing anybody. But what this outer negative for now means is to take the opposite. So the outer negative says take the opposite. So if I just focus on this negative 16 inside, that's our starting number, and the negative outside says to take its opposite. And the opposite of negative 16 would be positive 16. Oops, why did I do that? So again, we were focusing on the negative 16. We're saying that's our original number. The negative outside says to take its opposite. So the answer is positive 16. The opposite of negative 16 is positive 16. And if you know your rules for multiplication, then if you did the multiplication rules, you would get the same answer there. And again, I'm not going to say that yet. B. Now look at where this negative is. It's on the outside. It's not on the inside. So when we take the absolute value of 9/10, the negative is not in consideration. It's not going to go away. So the absolute value of 9/10 is 9/10. It was positive, so it stays positive. But now there's that negative on the outside, which we have to bring along. So our answer is negative 9/10. It's also like saying the opposite of the absolute value of 9/10. The opposite of an absolute value is going to make it negative. Spoilers for C and D, FYI. So C, we've got this extra negative outside again. So let's not focus on this negative yet. That's just going to say, oh, there's an extra negative in the end. So I'm only focusing on the absolute value of the negative 2.3. That negative that I have circled, I'm just going to bring along in a second. So the absolute value of negative 2.3 is positive 2.3. And in fact, let me illustrate this with color. Let me make that negative green, and you can see it there. So the absolute value of the negative 2.3 was this positive 2.3 in blue, but that green negative in front of it just gets brought along. So our answer is excuse me, I was about to read the question. The answer is negative 2.3. This is what I was alluding to earlier, that you can have problems with absolute values, but the answer be negative. That only happens when the negative is outside the absolute value, like in problems B, C, and spoilers, D. So with D, again, I'm going to leave this negative to the last second. I'm just bringing this along. For everything else, I'm thinking about what is the absolute value of the negative 21/51. Well, the absolute value of the negative is a positive. We leave the 21/51 alone. The absolute value of the negative blah, blah, blah is now the positive in red, but we had this green negative out front of it originally, so that's brought here. And that just says negative 2151. 21/51, excuse me. So again, you can have problems with absolute values where the answers are negatives. This only happens when there's a negative outside of the absolute value, because if the negative is inside, it gets processed and you get rid of it. If it's outside, it is not part of the absolute value. So there's a big difference there. All right. Oops. So I got to clear my screen. And we'll scroll down to the last, I believe the last problem for the day. A set of problems, that is to say. 16. Write in symbols, do not simplify. This is something that students miss so very often. The same issue with those exponent problems where you're supposed to write it as like 5 times 5 with 8 of those 5s and not actually find out whatever giant number that is. Something that would end in 5, no doubt. So the absolute value of 325. The absolute value of 325 is 325, but that's not what they want. They want you to write the absolute value symbol and put the 325 inside of it. That's what they're asking us to do here. They don't want to know that the absolute value of 325 is 325. They want us practicing how to write stuff. For B, the opposite of 18, we said the word opposite just means to throw in a negative, essentially. So 18, here's the original 18. But when we have the word opposite, so this word opposite tells us to put a negative in front of it. So negative 18. I just wrote too many ones. Negative 18 would be our answer. C, the opposite of negative 80. So you got to be a little careful here. There's a little more going on. This opposite word says you're going to throw a negative into the value. But the negative 80, we're not just writing an 80, we're writing negative 80. So it's negative 80. But we don't really like writing things this way. We don't like having two operations next to each other like that, especially with negatives. We typically wrap the negative 80 in parentheses like so in order to illustrate that. Now, yes, the opposite of negative 80 is positive 80, but that's not what they asked us to write. They said to write in symbols, not simplify. Then for D, they have the opposite of the absolute value. So the opposite word, that's going to be our negative that we'll toss in the front. And it's the opposite of the absolute value of negative 95. So negative 95 is what goes inside the absolute value. So here's our absolute value. And there's the negative 95 inside of it. And that is the answer. Again, if they asked you to evaluate or simplify, you would say, okay, the red part would be positive 95, but then you have that extra green negative out front. So the answer would be negative 95 if they asked you to simplify. They did not. They said to write in symbols, so that is our answer. So with that being said, we actually finished a few minutes early today. Nothing too crazy in this pair of sections, in my opinion. We've definitely done more complicated things, but it's also the first sections of the chapter, so I think it makes sense that things were a little simpler in concept. No dimensional analysis, no 4 or 5 different fractions being added, subtracted, multiplied, and divided. So just as a reminder, where was it? Here. So we finished 3.1 and 3.2, so those are going to be due by midnight of the next class, depending on whether you're the Tuesday, Thursday, or Monday, Wednesday class. Those are the due dates. Make sure that you are doing the separated parts for the Chapter 2 test, Part A, which is based on the first half, Part B, which is based on the second half of that chapter. But for chapter 3, we'll be doing the combined version. Again, I'm going to fix some things in Connect so that you won't even be able to access them, the parts that you're not supposed to access, that is. Remember to print your formula sheet from Connect, and we said that that was in, actually Connect's probably booted me out by now. Yep, it has. But that was under your resources course files, and it looked like this. So on that note, have a good afternoon, have a good day. Remember, this video will be posted on YouTube in about half an hour if you need to catch anything again or just slow things down. Please continue to work hard. Please take every opportunity you have in order to complete your homework in a timely manner. That way we can still pass this class. Have a good day.